Welcome to the deep dive. So, if you're someone who manages data, keeps things moving in servers these days, you know the game's changed,
Yeah.
right? It's less about how fast one drive is and much more about where the whole setup, the infrastructure. We've got these NVMe SSDs now capable of, frankly, astonishing speeds. We're talking, what, 10, 15, maybe even 20 gigabytes a second from just one drive. You'd think, okay, storage problem solved.
It really does create a fascinating paradox, though, doesn't it? The storage itself, the media, it's incredibly fast, plugs right into the PCI bus, super high speed. But then you try to, use that speed together, maybe in a RAID array for safety, and suddenly the traditional ways of managing that data, the controllers, they become the slowest link in the chain. That's the real choke point we're dealing with.
Yeah, it's like having a Formula One car, but you're stuck driving it on, I don't know, a bumpy country lane. The potential's there, but the road holds you back. So our deep dive today is into a really clever solution for this. GRAID Technology's Supreme RAID. And get this, it uses a dedicated GPU, a graphics card, to speed up RAID. Our mission here is to really unpack how this works, how leveraging a GPU fixes this old data bottleneck, what the actual performance gains look like, how fast is it, and, where you'd actually use this technology.
Exactly. This is all about tackling the I/O bottleneck, which, put simply, is just that point where your whole system slows down, not because the CPU is maxed out or out of memory, but because data just can't move fast enough between the computer and the storage. It's the plumbing, basically.
Okay, so let's start at the beginning. When did people first really notice that, hey, traditional RAID just isn't cutting it anymore with these new drives?
Well, that realization really started to solidify around, say, 2018. See, before NVMe drives became common, the bottleneck was usually the connection itself. SATA or SAS interfaces, they just weren't that fast. But NVMe runs directly over PCIe, which is way, way faster. Suddenly, the potential data flow just exploded. And the existing RAID controllers, both the hardware chips and the software methods, they just couldn't keep up. They were designed for the older, slower world.
Okay. So it wasn't the drives being fast that was the problem exactly, but the process of managing them, like the RAID calculations, the parity, the striping. That part couldn't keep pace.
Precisely. That's the core of it. It didn't matter if you had a dedicated hardware RAID card with its own special chip, or if you were using software RAID like MNDAB in Linux, which
Yeah.
uses your main computer CPU. Both methods just hit a wall. The software approach, well, it needed intense calculations for parity constantly. That absolutely hammered the CPU, stealing cycles from the actual work your server was supposed to be doing. And the hardware approach, that dedicated chip, the ASIC application-specific integrated circuit, it simply didn't have enough internal horsepower, enough bandwidth to juggle data from dozens of super-fast NVMe drives all at once, so that expensive hardware controller card, it became the new bottleneck.
Right. That's a really important point. The I/O bottleneck here wasn't just about slow data transfer. It was about the sheer computational load of managing data redundancy at these new, higher speeds.
Exactly right. And the founders of GRAID, they looked at this back in 2019 when they incorporated. Instead of thinking, let's build a slightly faster ASIC, which, would probably be outdated pretty quickly anyway, they asked a different, really crucial question. What piece of hardware do we already have, often sitting in data centers, that's specifically designed for massive parallel calculations? And the answer, maybe surprisingly, was the GPU, the graphics card.
And this is where it gets really interesting, that engineering leap. They decided to repurpose a graphics card, not for graphics, but for storage math.
They did. It was quite innovative. They realized the math involved in RAID, especially the XOR operations needed for parity in RAID 5 and RAID 6. Well, that kind of math is perfect for parallel processing. Think about it. A CPU has, what, a few really powerful cores, great for complex single tasks. But a GPU, it has thousands, literally thousands of simpler, specialized cores, perfect for doing lots and lots of relatively simple calculations all at the same time, like parity checks. And that insight led directly to Supreme RAID, which they launched officially in 2021. It just fundamentally changes how data protection gets handled.
So the company's mission became pretty clear then. Use software paired with this existing GPU hardware to just obliterate that I/O bottleneck. Turn this commodity parallel processor into, well, the fastest RAID engine out there.
Right. And to really get why it's so fast, you have to understand the shift in architecture. Supreme RAID is what you call software-defined RAID. It's primarily a software stack, a proprietary driver, but it crucially relies on having a physical GPU card installed to do the heavy lifting, the computation.
Okay, and the term that keeps coming up, the really defining thing, seems to be this out-of-path data flow. That's the secret sauce, isn't it?
It absolutely is. If you remember traditional hardware RAID cards, they physically sat in the path of the data. Every byte, every single bit, going from the CPU to the drives or back again, had to pass through that controller's chip, that ASIC. The ASIC did the checks, the calculations, the routing. And because everything had to funnel through that one point, well, that's where the traffic jam happened. That's the bottleneck.
Okay, let's try and visualize this out-of-path thing.
Hmm.
If the CPU needs to write data to the NVMe drives, how does GRAID stop it from getting stuck in that old traffic jam?
Okay, good analogy. Imagine the data moving from your CPU to the NVMe drives is like traffic on a massive, say, 100-lane superhighway, super fast potential. With traditional hardware RAID, every single car on that highway had to take an exit ramp, queue up at one single toll booth, that's your ASIC wait, while the toll operator, the chip, did its calculation, maybe stamped a ticket parity, and then get back on the highway. That single toll booth caused a huge backup.
Right, makes sense. So what does the highway look like with Supreme RAID?
With Supreme RAID, the main traffic, the actual user data stays on the 100-lane highway. It flows directly from the CPU straight to the NVMe drives. No stopping, no exit ramp. That's the out-of-path part. Now imagine there's a parallel service road running alongside the main highway. That's where the GPU sits. As the main traffic whizzes by, the GPU gets like a quick radio message, the metadata, the instructions for that data. It doesn't handle the data itself. And using its thousands of cores, like thousands of super fast toll operators working in parallel on that service road, it instantly calculates the necessary parity or checksum. Then it sends that parity data directly to the drives almost at the same time the main data arrives.
Ah, okay, so the GPU isn't slowing down the actual data moving. It's running alongside, handling the complex management calculations in parallel, super fast. It's like a dedicated math coprocessor just for RAID.
Exactly. Offloading that calculation is the absolute key. And we keep saying parallelism because that RAID math, the XOR stuff, it's simple but needs to be done millions of times. A GPU with its thousands of cores working together is just exponentially faster at that specific kind of repetitive task than the few, albeit powerful, cores on a CPU or an ASIC. And the beautiful result, your main CPU is freed up. It's not bogged down doing RAID math. It can focus entirely on running your actual applications, your databases, your VMs, whatever.
That division of labor, yeah, that makes total sense for optimizing performance. Okay, let's shift gears slightly. From an admin perspective, someone actually setting this up. It's mainly a Linux thing right now, focused on environments like Red Hat Enterprise Linux, RHEL. And I noticed they lean heavily on DKIMBus dynamic kernel module support. Why is that specific technical detail actually a pretty big deal for sysadmins? Because let's be honest, custom drivers can sometimes be tricky.
That's a really insightful question, actually, because, yeah, managing third-party drivers, especially kernel modules, can be a real headache in production environments where uptime is critical. Using DKIMs is a huge win for administrators. It basically automates driver compatibility during kernel updates. Think about it. Every time Red Hat pushes out a new kernel version, traditionally, you might have to manually recompile your custom drivers, or at least check if they still work, maybe wait for the vendor to release an update. It's risky, it takes time. DKIMs handles that automatically. When the kernel updates, DKIMs sees the Supreme RAID driver needs to be rebuilt for the new kernel, and it just does it seamlessly. It makes patching and maintenance so much simpler, reduces the risk of things breaking during an update, and just lowers the admin burden quite significantly.
Ah, okay. Less frantic recompiling after system updates, always a good thing.
Definitely. So once you have the prerequisites, you need a compatible GPU. Of course, NVIDIA is common. And the basic kernel headers for DKIMs to work the setup itself is pretty straightforward. It uses a simple command line tool, just GRAID. You want a super fast RAID 6 array. You type something like GRAID, create RAID 6, specify your drives, and boom, you're using thousands of GPU cores to handle the redundancy. It supports RAID 5, 6, 10 for performance and protection, and also the simpler RAID 0 and 1. All right, let's talk about the payoff, because ultimately it's the performance numbers that get data centers interested, right? When you remove that traditional bottleneck, that ASIC or CPU overhead, and you apply the GPU's parallel processing power, the metrics just go through the roof.
Okay, hit us with the key numbers. What kind of speed are we talking about?
Well, the documentation and benchmarks consistently show sequential read performance exceeding 100 gigabytes per second. That's GBCS. That's a valley.
Well,
It's not just an incremental improvement. It's a whole different league of storage throughput.
whoa, hang on. 100 gigabytes per second. Let's put that into perspective for you listening. Think about a big file, like a standard Blu-ray movie, maybe 50 gigabytes. You'd be reading 2 of those simultaneously in just 1 second.
Yeah.
That's unlocking the kind of speed NVMe drives always promised but couldn't deliver in RAID before.
Exactly. And it's not just about those big sequential reads. It also translates into millions of IOPS input-output operations per second. That's the number that really matters for things like virtual machine farms or big databases handling lots of small random transactions. And beyond just the raw speed, you get these efficiency gains too. CPU usage stays incredibly low because the heavy lifting is offloaded to the GPU. Plus, the performance tends to scale linearly. You add more NVMe drives to the array, the performance goes up predictably. That often doesn't happen with hardware RAID cards, which have a fixed internal bandwidth limit.
Okay, let me play devil's advocate for a second here. It sounds amazing, but aren't we just swapping one piece of hardware for another? We take out the RAID controller ASIC, but we add in a potentially power-hungry GPU. Doesn't that just shift the bottleneck? What about power draw, heat, needing an extra PCIe slot? How does GRAID stack up against those concerns?
That's a fair question, and it's exactly the calculation a data center architect needs to make. Yes, a GPU does consume power and needs a slot, but the key is the efficiency of the work being done. A traditional hardware RAID card, especially a high-end one, also consumes power, needs a slot, often requires proprietary firmware management, and still acts as a performance bottleneck, delivering only a fraction of the speed GRAID achieves. With Suprema RAID, you're using a standard commodity GPU. It's often more power efficient for the performance delivered. Because it processes the RAID calculations so incredibly fast, the whole system might actually spend less time under heavy load, potentially leading to overall power savings compared to a slower system that's constantly pegged.
Yeah.
You're using standardized, mass-produced compute power to do the job much, much faster.
I see. So the performance per watt, or maybe performance per dollar argument becomes pretty compelling. The GPU might draw power, but it does so much more work in that time that it can actually be more efficient overall, especially when you factor in the freed up CPU resources.
Exactly. Now let's compare it directly to the alternatives. First, versus traditional hardware RAID. The big drawbacks of hardware RAID are vendor lock-in, the high upfront cost of that specialized ASIC, and the near certainty that the ASIC will eventually become your bottleneck as drives get faster. GRAID offers a software-defined approach using standard GPU hardware that's generally more flexible, often more cost-effective, and bypasses the ASIC bottleneck problem entirely.
Makes sense. And compared to pure software RAID, things like Linux MDAD, the advantage seems obvious in terms of speed, but is there more to it?
Oh, much more. Yes, software RAID is cheap, maybe even free in terms of initial cost, but the hidden cost is performance. It absolutely hammers your system's CPU. It's not uncommon to see 30%, 40%, even 50% of your CPU cycles burned just maintaining the RAID parity, especially under heavy load. That leaves far fewer resources for your actual applications. Performance tanks. With GRAID, because the GPU handles all that, the CPU overhead is minimal, often near zero. But perhaps the biggest difference, especially for anyone managing critical systems, is rebuild time. When a drive fails in a software RAID array, rebuilding the data onto a replacement drive can take hours, sometimes even days, especially on large arrays. During that entire time, your array is degraded, performance suffers, and you're vulnerable to another failure. Because GRAID uses the GPU's massive parallel processing power, it can recalculate and rebuild that data incredibly quickly. We're talking rebuild times reduced dramatically, maybe by 10x or more in some cases. That's huge for availability and data safety.
Wow, okay. That faster rebuild time alone is a massive operational advantage. So linking this performance back, this isn't just for speeding up copying big files, is it? This tech feels aimed squarely at those really demanding workloads.
Absolutely. Think high-performance computing, HPC clusters, doing complex simulations. Think AI and machine learning, training huge models on massive data sets. Big data analytics platforms churning through terabytes of information. These are all environments typically starved for I/O performance. They need that low latency and high throughput. Also, high-end video production. Studios working with uncompressed 8K, 12K, even higher resolution video streams. They need guaranteed, rock-solid, high-bandwidth performance that traditional RAID struggles to provide without breaking the bank. #outro.
Okay, so let's try and wrap this up for you. The real takeaway here, the core innovation, it seems, is Djere taking a step back. They saw the NVMe bottleneck wasn't just a data pipe problem, it was fundamentally a computation problem at speed. And it solved it architecturally with this clever out-of-path software-defined system that uses the right tool for the job.
Right. They effectively transformed the GPU, something usually thought of for graphics, into this incredibly powerful, dedicated RAID engine. By leveraging its parallel nature, they bypass the limits, both physical and computational, of those older serial controller designs. It's just a really smart application of existing, powerful, commodity hardware to solve a modern data center challenge.
Yeah, it really does make you rethink how we can use the components we already have.
Yeah.
And that kind of leads to a final thought, something for you to maybe mull over. If a GPU can so effectively take over a computation-heavy task like RAID parity, freeing up the CPU, should we maybe start thinking of GPUs less as graphics processors and more as essential general-purpose parallel data processors for the data center? What other bottlenecks are lurking in our systems? Things like, I don't know, complex encryption or maybe data compression, even certain networking tasks. Could those also be massively accelerated by offloading them to a GPU's parallel cores? Could we reach a point where the main CPU mostly just directs traffic, while specialized parallel processors like GPUs handle the bulk of the heavy data lifting?
It's a fascinating direction, isn't it? The architecture of the future data center might rely heavily on processors we originally designed for something else entirely. We'll leave that thought with you.
Thanks for diving deep with us today. We'll catch you on the next one.